we recall what the projection of V2 onto V1 means and why we get this formula that people typically use without understanding or visualizing much of anything. Okay? Now, it just simply means if V2 is here and V1 is here, the projection is what we get if we project the tip of V2. We put V1 and V2 together so that the initial points are the same. And then we go from the tip of V2 down to the line of the V1 vector. I say the line of the V1 vector because it's possible that V2 is out in this direction. So we'd have to extend the line of the V1 vector in order to project V2 onto it. And you should know this already. We've done this. Okay, so what do we get if we do this? Well, we have a right triangle here. If this angle is theta, then the length of this side is called our scalar projection. Okay, now I say the length of this side. If V2 is in this direction, the scalar projection is going to be negative. So it's not really the length of the side, but the sine length of the side. So in this case, though, the projection is going to be positive because V2 projects onto the positive V1 direction. If V2 is back this way, it would project to the negative V1 direction. And the projection, the length of the projection, is just what? It's the adjacent side of a triangle of which V2 is the hypotenuse, or the magnitude of V2 is the hypotenuse. So the length of this scalar projection here, the length of this side of the triangle, is just V2 cosine theta. And I'm assuming that right angle trigonometry is pretty much second nature to all of us. Okay? It's V2 cosine theta, which is V2 dot V1 over the magnitude of V1 because, why? V2 dot V1 is magnitude of V2 times magnitude of V1 times cosine theta. If you divide out the magnitude of V1, you end up with magnitude of V2 times cosine theta. Now again, theta could be between 0 and 90 degrees, in which case this would come out positive, or between 90 and 180, in which case the cosine would be negative and the result would be negative. Okay. So we take the scalar projection now and multiply it by a unit vector in the direction of V1. And that's going to give us a vector whose magnitude is the same as that of the scalar projection. And that's going to be our vector projection. Now, I was a little careless when I wrote this down. I should have an arrow over this because I'm talking about the vector projection. Okay, so the scalar projection is V2 dot V1 over magnitude of V1, just by this right triangle and the property of the dot product. The purple vector here indicates a unit vector. Okay, and the unit vector in the direction of V1 is just V1 divided by magnitude of V1. There's our unit vector, so we multiply the scalar projection, the V2 dot V1 over magnitude of V1, by the unit vector V1 over magnitude of V1, and we get the vector projection. Now when we do that, we get V1 dot V2, or V2 dot V1, doesn't matter, divided by magnitude of V1 squared times V1, because, well, if you just multiply this by this, you'll see that you have V1 in the denominator twice. Now, I usually write this out, and I'm not sure why I didn't. So let me do that. I'm going to say, okay, that's V2 dot V1 over magnitude of V1 multiplied by V1 over magnitude of V1. This is my preferred form for the formula. Of course, it is equal to this, but this clearly shows your scalar projection times your unit vector. This disguises the fact that you're multiplying the scalar projection by the unit vector and gives you less information than this. And I prefer that you use this because it reminds you of what's going on. It reminds you of the geometry of the projection. This sort of disguises it, although if you know this well enough, you can see this in this expression. But if you don't see this in this expression, you're not reinforcing an insight that I think is very important when you talk about projections. Okay, well, that's what it is. Now, in the first problem, you're asked to project V2 onto V1, where V1 is the vector 1, 0, 0, and V2 is the vector 1, 1, 2, I believe. I'm not sure I wrote those down here. They're probably here someplace. Yeah, there. Okay? And of course, you have the documents. I'm assuming you're looking at the document. So it's very straightforward that the projection, the scalar projection, is 1. Projection of the vector 1, 1, 2 onto the vector 1, 0, 0 is just 1. We multiply that by a unit vector in the direction of V1, I'm sorry, and of course the magnitude of V1 is 1, but here are all the parts. Here's your V1 dot V2, here's your magnitude of V1, here's your V1, here's your magnitude of V1, matching all this, and we get this for our projection. Okay, now you're asked to calculate V2 prime, which is what you get when you subtract the projection of V2 onto V1 from V2. What's the significance of that? Well, if we look back at the picture here, here's your vector projection. Okay, in this case that would be your 1, 0, 0 vector. That vector plus the vector that runs along this side of this triangle has to equal V2. This plus this equals this. So that if we do V2 minus the vector projection, well, vector projection plus this equals V2. This has to then equal V2 minus the vector projection. And you can draw a picture of that. In this case, if this is your projection, then we have this triangle. Here's your V2, and if we do V2 minus the projection, what we're doing is V2 and minus the projection gives us this vector here. That's the vector we're trying to find, and it's identical with the vector that you would have here. Again, I'm not explaining this in complete detail because we've done this, but you need to understand that what we're effectively doing here is taking the part of V2 in the direction of V1 and subtracting it off. And what does that leave us? It leaves us the part of V2 that's perpendicular to V1. We just throw away the part of V2 in the direction of V1, and we're left with something, a vector that's orthogonal to V1. So V2 prime, which is going to be the vector we're trying to find here, is just V2 minus the projection. Here's your V2, here's your projection, and here's what you're left with. Okay, now we'll go on with this in the next clip.